Can we solve quantum chemistry problem on a quantum annealer? This is a question that is addressed in the paper that I will highlight in this video. So let's start with the problem itself. So quantum chemistry tries to solve the electronic Hamiltonian eigenvalue problem. And usually electronic Hamiltonian, for the purpose of using quantum computing, can be first expressed as like in fermionic operators right here with the 1 electron, 2 electron integrals. And then using qubit fermion mapping like Jordan-Wigner mapping or Bravik-Kitaev or any other mapping, it's then transformed into the qubit Hamiltonians isospectrally. And that transformation essentially produces the operator which has Pauli products in general of different qubits, and the subscript here for the sigma will mean the qubit that operator is acting on, and the superscripts corresponding to x, y, z, or identity in some cases. So essentially there is this linear combination of the products that you obtain after these mappings. All right, now what do annealers do really? This is a somewhat different technology than gate computing, but in the kind of without any constraints, it can be shown to be equivalent. And of course, real architectures has some constraints. And the main idea behind annealers is that they can drive a quantum system from the initial Hamiltonian to the final one with the purpose of starting with the eigenstate of initial Hamiltonian, which is easy to prepare because the initial Hamiltonian usually is very simple, to the eigenstate of the final Hamiltonian that is of interest and non-trivial. Now, the way it works for at least D-wave is that the initial Hamiltonian is where all the qubits are under the action of the magnetic field in the transverse direction, in the x direction. That's why the Hamiltonian can be simply written like this. And then the final Hamiltonian is also sort of Ising type, where each qubit, there's linear part where each qubit essentially experiences the Z local magnetic field, and then there are ways to couple Z components of each qubit for these J terms. And finding the lowest eigenstate of the final Hamiltonian is not such an easy task because you need to essentially flip all the qubits Z orientations up and down in order to search for the lowest state. Now, what D-wave does, it starts with the initial state of the simple Hamiltonian, where we know what the lowest eigenstate is. It's all the qubits are oriented along the magnetic field. And then if we slowly, on a micro scale, transform the Hamiltonian from the initial to final, then we evolve the ground state of the system from this simple product state to the collinear orientation of all the qubits along the z-axis, and that essentially follows the adiabatic theorem of quantum mechanics and assumes that there is always a finite gap between the ground state and the excited states of the system. So this is how it works, and at the end we can obtain the ground state of the Ising Hamiltonian with the quantum annealer. Now, if we compare this with the electronic Hamiltonians that we have in the electronic structure problem, then you can see easily that there are a few differences. First of all, the number of terms could be bigger, and the products of the Pauli operators can go from quadratic to the higher powers all the way up to n, really where n is the number of orbitals in the system. And so it doesn't stop at the quadratic level. And even more challenging aspect is that the Pauli operators that we have in the qubit Hamiltonians from molecules, they can contain not only Z terms, but X and Y as well. And that, of course, produces more complicated eigenstates for the electronic Hamiltonians. Now, if someone wants to generate the solution for the electronic Hamiltonians on a quantum annealer, a natural idea would be somehow map the electronic Hamiltonian to the Ising Hamiltonian. And that's a challenging task, but it turns out bridging those Hamiltonians is possible. And a group of Saber guys relatively recently published a work, I think it's published in Journal of Physical Chemistry A, where they shown that the mapping is possible between the Hamiltonians, but it produces essentially exponential growth of the Ising Hamiltonian when you increase the size of the system. So it's a difficulty, essentially. So in our work, we decided not to bridge the Hamiltonians and use quantum annealers quite differently. We would like to use quantum annealer just to optimize energy function that appears in one of the methods that we developed, not for the annealers, but for actually universal gate quantum computing. And the method is qubit coupled cluster method. Let me tell you a little bit about the qubit coupled cluster method. You, of course, can learn more from my previous videos or reading the papers we publish on that method. And the idea of that method is to solve the variational quantum Eigensolver problem of optimizing the unitary transformation, and the gate-based computing is organized somewhat differently. So here we start with some initial state that we rotate using unitary transformation. That qubit coupled cluster method is kind of helping to develop, right? And then at the end, we have a wave function that we measure the Hamiltonian expectation value on. And based on that expectation value, we try to correct, to optimize our unitary transformation that we use for preparing the wave function. And this is like a feedback cycle that will generate eventually optimal unitary transformation that lowers the expectation value of the Hamiltonian. On a formal level, this is a minimization problem we're trying to solve. And we're solving it with respect to the amplitudes of the unitary transformation. Now, we consider unitary transformation as a product of those type of exponents, where there are amplitudes, tau, and p's are operators that multi-qubit products of just individual qubit operators, sigmas. Now, there is an exponential number of such products, and the natural question is which ones to choose to drive the energy lower if you optimize the amplitudes. And it turns out that the gradient search is very helpful. So the gradient of energy with respect to the amplitudes given by this simple expression at the value of the amplitude is equal to 0. So you can use that expression to find the products that are the most efficient to drive the energy down. And also this still doesn't address the question of the exponential number of the products, but it turns out that on the kind of intuitive level, what this expression is the qubit version of the Condon-Slater rules. And we know in the Condon-Slater rules, because the Hamiltonian is just a 2-electron Hamiltonian in the electronic structure theory, then the number of non-zero gradient essentially operators is somewhat limited to polynomial number. So in this case, it's also true, and it turns out that there are ways to screen the products in a polynomial way, so you don't need to go over the exponential number of possible products to find the ones that are the most important. So the details are again in this paper that you can take a look at. Now, alternative way of looking at this as we call them, entanglers, the components of unitary transformations, the exponent of products, is that we apply them not on the wave function, but on the Hamiltonian. So we transform the Hamiltonian, and it's like a Heisenberg type of view of what's going on, compared to a Schrödinger view where you put the unitary transformations on the wave function. Here we put them on the Hamiltonian. Turns out this is formally known as a Baker-Campbell-Hausdorff expansion. For the case of multi-qubit Pauli products, this BCH expansion truncates naturally very quickly, and we can essentially formulate the transformed Hamiltonian as an operator depending on the amplitude for the particular entangler, right? And the truncation property just really comes from the algebraic property of these P operators. They have involutory property that P squared is equal to 1, and that generates short expansion. Now, if we keep applying different P's that potentially can drive the energy down, we can transform the Hamiltonian further and further, generating it as some operator function of taus. And if we contract this with like a elementary product wave function zeros, which can be considered as like a qubit implementation of Hartree-Fock Slater determinant, then we can obtain the energy function. All this can be done analytically. The only problem is that, of course, with the number of entanglers, the expression grows exponentially. So to mitigate that exponential growth, we recently found another way of formulating the operators that are used to so-called transformational dressing of the Hamiltonian. And that's probably going to be a topic of the next videos. For now, we can admit that indeed the energy function grows exponentially with the entanglers, and the game here is to find few entanglers that will not create a very large energy function, and still that energy function will provide accurate approximation to the ground state energy if you optimize all the amplitudes. Okay, so the problem here now is to optimize the amplitudes, and for that we'll use the annealer. Now, before we formulate how exactly the annealer will be useful, the first step in the process is to really introduce the integer variables in the optimization process. And the idea here is that the energy function is a relatively straightforward linear combination of trigonometric functions like sine and cosine, functions of amplitudes. And then there is a way to reformulate this optimization problem from purely continuous variables, which are amplitudes, to integer continuous form, where we introduce integer variables that will be optimized on the D-wave part of the problem. Okay, now how do we introduce these integer variables, and why is it useful? Turns out that you can use symmetry of trigonometric functions so that introduction of these integer variables will reduce the domain of continuous variables. That's the gain, right? So let's see how it works. If we consider, say, functions that we have in the energy expression, sine and 1 minus cosine, and then the blue is a sine and the red is 1 minus cosine divided by 2, and you can see that all the values of, say, 1 minus cosine function, you can obtain all unique values. You can obtain by going just from 0 to pi. You don't need to go from 0 to 2 pi, because in the second part of the domain, you get exactly the same values as in the first part. Therefore, you can just look for the amplitudes within the first part. Now, with the sine function, the story is different, because in the first part of the domain, from 0 to pi, you will only obtain the positive values of the sine. but in the second one, it's you will obtain the corresponding negative ones. But the negative ones are exactly like the positive ones, just with a minus sign. So technically, you can consider sine function in the full domain, 0 to 2 pi, by restricting it from 0 to pi and introducing the second branch. So the second branch is essentially a reflection of the first one in the x-axis, or the tau axis in this case, right? And in order to switch between the two branches, if you want to potentially have access to both of them, you introduce integer variable. And the integer variable is naturally plus minus 1. So what you achieve by doing this step is that you reduce the domain for the amplitude from 0 to 2 pi to just a half of it, 0 to pi. Okay, so then it turns out you can do a next step and fold the domain even further to just a quarter of the initial domain. Why? Because if you look what values of the functions you're going to get for the first part, 0 to pi over 2, then you will see that both branches of the sine, they will already generate all the values, because the second half essentially repeats. It's a mirror image around the pi over 2 point, right, of the first part. And that's why you can just consider the first half of our reduced domain, and you don't need to introduce anything else. But on 1 minus cosine over 2, you will need to introduce an extra variable, so that because there is a second branch appearing if you fold this function around the pi over 2 point. So in order to essentially reduce the 0 to 2 pi domain to just a 0 to pi over 2, quarter of the initial, you need to introduce two variables which are the discrete nature, plus minus 1, for those two functions. And that idea is essentially crucial to formulate the continuous optimization problem as an integer continuous optimization. And it achieves the reduction of the continuous amplitude domain. And the more amplitudes you have, the larger the gain, essentially, because you are gaining exponentially with the number of amplitudes that you use in this technique, right? So the more taus you have, the bigger the advantage. All right, now how do we turn this all into the something that we can use quantum annealer for? The quantum annealer naturally is finding the eigenstates of the Ising Hamiltonian. So these f and g variables that we introduce, they can be really seen as z operators, Pauli z operators. And the optimization process can be seen as now finding the lowest eigenstate of this generalized Ising Hamiltonian. Why generalized? Because when we do this folding, we introduce an f and g functions, which we substitute by Pauli z operators, right? So here I just redefined for like a short notation. Instead of sigmas, I'll be using z's, right? And your energy functional becomes like an operator with lots of z's because you have a lot of integer variables once you do the folding. And the power of those z's can go above the quadratic one, right? And you essentially obtain so-called generalized Ising Hamiltonian. And now the problem is, how do we make Ising Hamiltonian out of this generalized Ising? Turns out this is possible too if you do the grouping of some z's. So if you take the two z's and make like a fictitious new qubit, the big Z, ij. And the only problem, if you keep doing that, you will reduce, of course, the power of your Z operators. But the new fictitious qubit need to be coordinated with the ones that are still with the old ones, essentially, right? And for that, we use penalty function, which is a 0 when the values of the these new fictitious qubits are exactly correlated with the values of the old operators, right? And it's positive if there is some deviation, right? So you kind of penalize for this big Z to be different than the product of small z's. So the details are reported in this paper where this penalty was first introduced. All right, so if you do that penalty, you essentially introduce only quadratic terms and linear terms. And so by grouping those z's, you can essentially obtain the Ising form. And now you can translate the optimization of the energy functional into solving the Ising problem on the D-wave. Now the way it works, first we look at our electronic Hamiltonian, transform into the qubit space to the qubit Hamiltonian, then decide what QCC ansatz, what is the unitary, what are the multiple qubit products we use for that unitary, and to formulate what the energy function is in terms of amplitudes. Then do the kind of the folding of the domain, introduce new discrete variables, substitute them by the Z operators, do the kind of obtaining the Ising Hamiltonian. And once we have the Ising Hamiltonian for the energy function, we do the like a two-step optimization procedure where first we optimize, say, all the continuous variables over the reduced domain on a classical optimizer. And then once it's like optimized this function of continuous variables, then we do the integer optimization using D-wave by finding the lowest eigenstates of the Hamiltonian that we prepare out of the function. So that allows us to fix at optimal values the discrete variables and optimize again the continuous part. And so these circles between the continuous and integer variables allow us to eventually obtain the global minimum for the function of energy. Okay. Now here's an example that compares this procedure with just something that doesn't use domain folding. And the main goal is to be able to obtain the global minimum of energy in the space of amplitudes for the entanglers. Now we considered just two systems, relatively simple ones, lithium H, and a little bit more complicated one, the water, that is stretched. If you stretch water along the two coordinates, OH bonds, then it becomes a more challenging system. And what we did here is like 100 trials, optimizing from different initial amplitude values, trying to find the global minimum of energy expression. For the continuous optimization, we use a BFGS type of approach. And then there are, within these 100 trials, there is a success rate for both molecules. How many times do we obtain what we know is a global minimum for the extensive search? Turns out that out of 100 trials, like for lithium H, if you just don't do any smart tricks, just do continuous optimization of energy, you will optimize to a global minimum only less than a fifth time, it's less than 20%, okay? And then if you do the same experiment for water, it's just close to 2-3% chance of getting the global minimum out of this optimization. Now, if you do domain folding, either here we present several domain foldings, and the main difference between this set of experiments is like how many foldings do we do, because every folding, of course, introduces the integer variable. So at some point, this exceeds capabilities of the D-wave, right? So we had limited possibilities for folding. That's why in D-wave case, we didn't do as many foldings as what we call ideal Ising machine, where we allow ourselves to do as many foldings as we want. That, of course, will produce many Z variables and higher powers, but we don't want to reduce these higher powers, since we can use classical computer for simulating those high powers. But going to D-Wave would require grouping some of these terms into the fictitious qubits, and that will exceed the current capabilities of D-Wave, at least, right? So that would allow us to do fewer foldings in general. But the overall picture is quite clear, is that when you do foldings, especially these numbers essentially correspond to the number of foldings in the different parts of the energy expression, you can see that the chance of getting global minimum is much higher when you do foldings of various kinds. And that's kind of the main message. The details, again, you can look up in the paper. Now, to summarize, the main challenge of doing quantum chemistry on a quantum annealer is that the qubit Hamiltonian that you get in electronic structure problems usually mismatches the Hamiltonians that D-Wave and other quantum annealers can essentially handle. Because the ones that appear in quantum annealer, they are of Ising nature. And therefore, we decided in our approach not to try to bridge those Hamiltonians. They are very different, but instead use the annealer to make more efficient energy optimization in the QCC approach, because their energy is just simply can be written as a linear combination of some products of trigonometric functions that have certain symmetry. And so you can reduce the domain and introduce integer variables that then you can optimize as a part of the kind of finding the global minimum of the Ising Hamiltonian. Now, one challenge in our approach is that accuracy depends, of course, on the unitary transformation that we use to obtain the energy in the QCC approach. And with more entanglers, more Pauli products, that energy expression grows exponentially. We have somewhat a mitigation technique for that, and hopefully we will consider it in the next videos. So stay tuned.